Modern networks reveal a visual paradox. Rather than an even distribution of connections, a massive web of nodes organizes around a few centralized hubs. Historically, mathematicians modeled networks using the Erdos-Rényi, or ER random network model. The ER model operates under a static constraint. The total number of nodes in the system, denoted as n, is fixed. Inside that fixed system, links are added uniformly and randomly. Every pair of nodes has an equal probability of being connected, without bias. These constraints force the ER model to produce a Poisson degree distribution, essentially a bell curve. Most nodes have a degree close to the average, making massive hubs mathematically impossible. Because it relies on fixed nodes and uniform links, the ER model fails to account for the massive hubs found in the World Wide Web. In real-world systems, the probability of finding a highly connected node does not decay exponentially. It follows a power law. To accurately model scale-free architectures, a system must be viewed as a result of a growth process that operates over time. The first dynamic rule is growth. Real networks expand through the continuous addition of new nodes. The second rule is preferential attachment. When new nodes arrive, they are biased towards connecting with nodes that are already highly connected. The Barabasi-Albert, or BA, model serves as the mathematical unification of these two axioms. This unified approach results in the emergence of a scale-free topology, characterized by a stationary degree distribution. Growth and preferential attachment are the mechanics required to explain why highly disparate systems, such as the World Wide Web and the cell, converge to a similar scale-free architecture. We derive the BA model using mean field theory. A new node arrives with m links. Preferential attachment dictates its connection probability, pi, is proportional to existing node degree, ki. We track this evolution using a rate equation. Integrating this rate equation allows us to solve for ki of t, showing that the degree of each node increases as a power law of time. To find the degree distribution for the entire network, we integrate over the arrival times of all nodes. Assuming a uniform probability density of arrival times, this integration reveals the final degree distribution, p of k, which follows a power law. Mean field theory demonstrates that continuous growth and linear preferential attachment force the network into a scale-free state with a degree exponent of gamma equals 3. While mean field theory identifies the correct scaling, it is an approximation. It provides an incorrect coefficient for the degree distribution, particularly for small k values. A precise solution requires a rate equation approach, which accounts for the discrete nature of the nodes and links. This log-log plot shows the degree distribution. As the degree k increases, the data forms a straight line, confirming that the power law behavior remains invariant as k approaches infinity. We test the necessity of these axioms by isolating them. In Model A, we maintain growth but use uniform random attachment. Without preferential attachment, Model A fails to produce a power law, resulting instead in an exponential degree distribution. In Model B, we use preferential attachment but keep the number of nodes fixed. It briefly mimics scale-free behavior before the distribution collapses into a Gaussian curve and eventually a fully connected graph. These tests prove that a stationary scale-free state requires both growth and preferential attachment to operate continuously. Linear preferential attachment seems to require that every new node knows the degree of every other node in the network. However, local elements, like a single web page, lack this global knowledge. The copying model provides a localized mechanism that generates preferential attachment without requiring global information. First, a new node connects to a randomly chosen target node, U. Second, the new node links to one of the nodes that U already points to. It copies a link from its target. Because high-degree nodes are more likely at the end of a randomly selected link, this two-step local process is mathematically equivalent to linear preferential attachment. Empirical data from citation and collaboration networks confirms this. These plots of the preferential attachment integral show a linear relationship, matching the kappa sim k prediction. Global architectures emerge spontaneously from these local copying pairs, requiring no central coordination. We can also analyze the local density of these systems through the clustering coefficient, C of n. In the BA model, clustering is defined strictly by the probability of 3 nodes forming a closed triangle. To find the expected number of triangles, we integrate the connection probabilities between nodes I, J, and L. The resulting clustering coefficient is a function of the system size, n. While the BA model clusters more densely than a purely random graph, its density still decays as the network grows. This indicates that while the BA model accurately predicts degree distributions, it does not fully capture the high levels of social clustering observed in human networks. The transition from the static model to the dynamic BA model represents a shift toward understanding how networks evolve. The core of the model lies in 2 axioms: networks must grow, and new connections must be biased toward highly connected nodes. These rules lead to a stationary, scale-free state with a degree exponent of 3. For students of network science, there are 3 common pitfalls to avoid. First, the stationary state illusion. Although the network size n increases over time, the probability distribution P of k remains stationary. The relative proportion of hubs to smaller nodes does not change. Second, the mean field shortcut. Mean field theory is useful for finding the degree exponent, but it is an approximation. Precise calculations for small nodes require exact rate equations. Third, the omniscience fallacy. Preferential attachment is not the result of nodes having a global map. It is an emergent property of local rules, like copying a neighbor's connections. The Barabasi-Albert model demonstrates that the massive hubs of the World Wide Web and the cell are not random accidents, but are governed by predictable laws of growth.